if we have a system of two point masses m1 and m2, then their gravitational potential energy U is given by minus g m1 m2 divided by r. We are going to derive this formula, and we will not make the use of calculus or integral calculus in this derivation. The potential energy is defined by the amount of energy, amount of the work we need to do to constitute this system. So imagine this mass m2 is lying at infinity, and we are trying to bring this mass m2 to this position, which is at a distance r from m1. There is a force of attraction between m1 and m2. The m1 is already pulling that m2, so we don't have to do any work. In fact, we will actually get some work when we bring this mass m2 closer to m1. On the other hand, if we take this mass m2 away from m1, then we will have to do some work against the force of attraction, and we will have to do some work to take it from this position to infinity. We will derive this formula by taking this mass m2 from this position to infinity, find the positive work we have to do, and then multiply it by minus 1 to get the gravitational potential energy formula. So the force between these 2 point masses is given by F equal to g m1 m2 divided by r square. Let's say we take this mass from this position, which is at a distance of r, to a very small distance, which is at a distance of r1 from this point. We will have to do some work, and that work is given by this force F multiplied by r1 minus r, because work done is equal to force into distance. Now we have this work g m1 m2 multiplied by r1 minus r. As we take this mass from this position to this position, the average distance between these two is not r, it's not r1, it's somewhere in between r and r1, and that is r1 plus r divided by 2. Now we use a special mathematical trick, and the trick is, if there are two numbers a, x and y are very small, then their arithmetic mean is the same as, about the same as their geometric mean. This is the arithmetic mean, and this is the geometric mean. So these two values will be very close. For example, this is 2 and 2.01. So whether you find their arithmetic mean or you find the geometric mean, they are going to be about the same. And we can derive if you want, if you are interested. Here is, I have shown it how it is that. Let's say the geometric mean, the arithmetic mean is this, the geometric mean is this one. And we have squared this thing so that to make it easy to understand, to make sure to do away with the negative values. So this is x plus y divided by 2 whole square minus the geometry square of the geometric mean. This is x square plus y square plus 2xy, and then the whole thing is divided by 4 here, minus xy. If you rearrange these terms, you get x square plus y square divided by 4, 2xy minus 4xy is minus 2xy divided by 4. This becomes x minus y whole square divided by 4. So this numerical value of this difference between the arithmetic mean and the geometric mean is given by x minus y by 2. I take this mod of this. If these two numbers are equal, then we see that there is no difference between the arithmetic mean and the geometric mean. So coming back to here, the amount of the work done, W1, when taking this particle from the position R to R1 is given by G M1 M2. R1 minus R is the distance that it traveled from R to R1, divided by R1R, which is the average of the distance between these 2 points. we can divide this R1 divided by R1R, it becomes 1 upon R. R divided by R1R is 1 upon R1. In the same way, we can find the work done when taking the particle, the mass m1, from position R1 to position R2 in the same fashion. We call it W2, G m1 m2, R2 minus R1 divided by R1 R2. Or simplify this again, we get W2 equal to G m1 m2, 1 upon R1 minus 1 upon R2. In the same way, we find the work done from R2 to R3 as G m1 m2, 1 upon R2 minus 1 upon R3. And we can continue doing this, and we got final. Let's say we take the position nth position, we have G m1 m2, 1 upon Rn minus 1 minus 1 upon Rn. The total amount of the work can be obtained by adding these works W1, W2, W3, Wn, which will give us the amount of the work done in taking the particle from position which is at R to a position which is Rn. If you look closely, you see if you add all these terms, you see that 1 upon R1 minus 1 upon R1 cancels with minus 1 upon R1 here. Minus 1 upon R2 cancels with this. And same this continues this whole thing. In the last we get minus 1 upon Rn. So the amount of the work done from the position which is at R equal to R equal to Rn is the sum of these, and it's given by Gm1 m2 1 upon R minus 1 upon Rn. And therefore, if Rn tends to infinity, this term becomes 0, tends to 0. And therefore, the work done will be given by W is equal to Gm1 m2 divided by R, and the potential energy is given by negative of this work done, or minus Gm1 m2 divided by R. You may also want to check now the trick is a faster method using calculus. But if you have not done a course in calculus, you may use this method as well.